Welcome to the second day of this forum. My name is John Grassel, and I once again will be your moderator. I am a forensic science program manager at RTI International and serve as the co-principal investigator for the National Institute of Justice's Forensic Technology Center of Excellence. This no-cost virtual Firearm and Toolmarks Policy and Practice Forum is brought to you by the National Institute of Justice and the Forensic Technology Center of Excellence. Presentations will revolve around four main topic areas related to forensic firearm and toolmark analysis. These include research, intelligence, legal aspects, and today's topic, which is emerging technologies. Following the presentations, a panel of presenters will come together for an interactive question and answer session. On the forum's final day, January 14th, we plan to hold a special panel discussion that will focus on the next steps within the field. Our keynote presenter today is Dr. Ryan Lillian, who will discuss emerging 3D technologies in firearm and toolmark examination. Dr. Lillian's research expertise focuses on the use of advanced scientific computing and statistical models to solve interdisciplinary research problems. He earned an MD and a PhD from Dartmouth Medical School and Dartmouth's Department of Computer Science. Dr. Lillian was faculty at the University of Toronto, cross-appointed between the Department of Computer Science and the Faculty of Medicine. Now at Cadre Forensics, he leads the development of the top-match 3D high-capacity system. For the past 8 years, he has presented his group's steady progress on developing and validating the system at national and regional Association of Firearm and Toolmark Examiners meetings. Dr. Lillian has provided instruction at the National Firearms Examiner Academy, regional training seminars, and within individual labs. He is currently a member of NIST OSAC Subcommittee on Firearms and Toolmarks. Welcome, Dr. Lillian.
Okay, so we're going to get started here. So you can see, hopefully, my video, as well as you can see my snapshot on the first page here. My name is Ryan Lillian, and as you heard, my background is in computer science. And we've been working over the last 7 or 8 years or so in developing tools for 3D virtual comparison microscopy within firearms and toolmarks. And so in today's presentation, what I want to hit are a couple ideas in emerging technologies, 3D technologies in specific, for firearm and toolmark examination. A lot of the work and projects I'm going to talk about are in collaboration with my team. And you can see some of the team here. So there's myself, Chad Chapnick, Eric Meshke, Pierre Duez, and we do a lot of collaborations with Todd Weller at Weller Forensics. He's a firearms and toolmark examiner. And you heard from him yesterday in a presentation, which has a little bit of overlap with what I'm going to tell you about today. So I need to give a standard disclaimer that some of what I'm going to talk about was supported by grants from the National Institute of Justice, and everything I'm talking about today are our opinions and thoughts and not those of the funding agency. So as I said, I want to talk about emerging technology of 3D virtual microscopy within firearms and toolmarks and how it can be used in the lab. And I know that some of the other presentations are obviously hitting on it. It's kind of one of the big themes. Yesterday, you heard a bit about, like from NIST with Brian Renegar, about 3D imaging and how we can ensure that the 3D measurements we get are actually accurate. Todd Weller probably spoke about some software tools and how that can be used from the examiner's perspective, and I'm going to hit a little bit of that. And Hans Soons from NIST spoke about scoring and how we can come up with a grounded statistical score. So I'm going to kind of tie a lot of those components together at a higher level view and then fill in some details. And as I do that, I'm going to talk also about some of what I think is going to happen over the next couple of years. So I'm going to start with a little bit of background and the transition into 3D measurements. Some of the uses for 3D virtual microscopy within the lab, and most of these uses that I'm going to hit today are things that some labs are actually using today. This is not a 5 or 10 years, this is happening now. Some of the validation work that's been done to ensure the high quality of the work product that comes out of these new tools. We'll talk about some insights that you can gain from virtual microscopy that maybe you wouldn't necessarily have with a traditional microscope. And then in the last 15 minutes, we're going to focus on comparison algorithms. Just hinted at a little bit, perhaps in Hans's talk, but how can we use these algorithms to augment the work product? And this falls into 3 categories. The first is database search, The second is coming up with a statistical score. And the third is just facilitating the examination process. And then, of course, I'll try to tie it all together. So to get us all on the same page, jumping right in, you know, of course, that what a firearms and toolmark examiner will do is they will get an envelope of evidence, and they will look at specimens from crime scenes and from suspect firearms, and they're going to be looking at bullets and cartridge cases that have been discharged, and they're going to look at the tool marks that have been imparted on those items. And we can reach conclusions regarding things like the number of firearms that may have been present at a crime scene, perhaps the makes and models of some of those firearms based on looking at some of the class characteristics. And we can match perhaps a suspect firearm to actually being at the crime just by doing these intercomparisons. We're going to talk about how that's done. Another use, of course, is to take examples from the suspect's firearms, so test fires or items from a crime scene, and hit it against a database. So compare those images against images that have been previously collected from other incidents, and perhaps link a suspect or a current crime to something that may have happened in the past, and then follow up with that as an investigative lead. So to be able to do this, there are a number of marks that a firearms and tool marks examiner will look at on both the bullet and the cartridge case or the shell. We're going to talk primarily about cartridge cases today, although all the software tools I'm describing can equally be applied to bullets as well as to cartridge cases. I'm just using cartridge cases as some examples. And there are certain types of marks that we want to look at. And again, without going into all the technical detail, there are breech face marks shown here in the red highlight, aperture shear marks here in orange, and firing pin marks in green. We're going to talk, I'll show you a bunch of examples about aperture shear, and the way the aperture shear is formed, if I go to the next slide, is kind of like a rake in sand, right? So depending on the spacing of the teeth or whatever it is called in the rake here, as you pull that rake through the sand, you're going to get different spacings of these lines. Similarly, as the cartridge is fired through the firearm, there is a metal surface that scrapes against another metal surface and scrapes the first surface in a way very similar to the rake in the sand. So here on the left are images of two cartridge cases that were fired through the same firearm. We call that a known match comparison. And you can see these horizontal striation lines, and you can see that the item on the left and the item on the right have continuation of those lines. The lines go straight across, and most of them match up. This is an image from a 2D microscope, a traditional comparison microscope that we'll talk about, not the 3D technology that I'm going to show you more. On the right is a non-match. So a known non-match is two specimens that were discharged through different firearms. And you can usually see maybe one or two lines of commonality just by random chance, but the vast majority of the striations on the left do not line up with the striations on the right, and therefore this is a non-match. So these are the types of comparisons that a firearms and toolmark examiner is going to make when looking at these microscopic surfaces. So about 100 years ago, it was observed that these microscopic marks could be used to determine common source. Calvin Goddard is one of the kind of fathers of the discipline and first made use of a comparison microscope here. And I believe you've seen a picture of this yesterday. So here you see two comparison optical paths going for, above two specimens being combined, and then the operator can see the two specimens side by side. And over the last 100 years, we've basically developed this same technology into a more modern scope. But even in this more modern scope, we essentially have two optical paths being combined into an eyepiece or maybe a digital camera connected. After we had these nicer, more powerful microscopes, we also were able to take those digital images and either compare them, whether print them out or compare them digitally to find the links and connections. Initially, that was actually done with a stack of Polaroids. So you would take an image off of your scope and then go over to a file cabinet and flip through to find similarity between your item and something from the past. And then, of course, you'd pull out the actual specimen, take them over to the actual comparison scope and look at them. Now, this all set the stage for essentially the first digital networks. And about 30 years ago, the FBI, working with a company called MSI, developed the first one of these, which is called DrugFire. And it used these 2D side-lit images to basically do this comparison automatically. And here's some kind of these from the archive images. So you can kind of see there are two surfaces here, kind of blurry, but this is a kind of a junky screenshot. In reality, it would have been a bit sharper. And then, of course, you have a computer here that can do those comparisons. At the same time, the ATF is working with a different company called Forensic Technology, and they came up with the IBIS system, which has now evolved into the NIBIN system, which is still around today. But the basic idea, again, is the same as fundamentally from 100 years ago. We're going to examine microscopic surfaces. We're going to compare two at a time. We can take images of those and compare them to historic cases and see if we can find connections. So this is where we were up until the early 90s. Actually, this is where we were up until about 8 years ago. And about 8 years ago, we started thinking about 3D imaging in firearms and toolmarks. In fact, it was actually about 15 years ago that the first use of this term was introduced. So the 3D virtual comparison microscope, at least to my knowledge, the first reference to that phrase was this Journal of Forensic Science paper from 2006 by a group of Italian researchers. It's a really neat paper, especially because it was so kind of ahead of its time in terms of using 3D microscopes. At the time, things like confocal microscopes, but within this new application domain. Here's a figure from their paper, and what they describe for virtual comparison microscope is a system where there's an image acquisition half and an image analysis half, right? So here's 3D acquisition using some fancy microscope. We collect the measurement data, shown here in the middle, and then we can take that measurement data over onto another system. That computer could be the same computer or somewhere down the hall, and we can view those surfaces and do some type of a comparison. And we would do this in much the same way that we would use a traditional microscope, but now we're doing it in this kind of virtual way. Instead of actually looking at the physical cartridge case, we're looking at the 3D measurements of that cartridge case. So if we do that, we get a surface that might look like this. Let me zoom in a little bit. So this is a scan off of the system we've been developing. You can see a lot of surface detail. This is the NIST standard cartridge case. The NIST standard cartridge case was selected by NIST as a standard reference material in SRM because it's very well marked. And so most cartridge cases are not going to be as well marked as this, but it's a great example from the imaging perspective of this is what you would see if that information actually exists on the surface. You can see some scale bars at the top. So here's a 30 micron scale bar, and you can see how large that is for some of these features that you're looking at. Now in this image, it's scanned at about 1.5 microns per pixel. Typically systems today are closer to 2 or so microns per pixel. There's a trade-off that we don't really have time to go into today. Now, I'm not sure how well this appears on your computer screen because, of course, this is a measurement that we then visualize in our software. We then capture a screenshot. I've now put it into presentation software, and now we're doing it over a presentation remotely. So hopefully it looks really sharp to you, but it definitely looks better in person when you're sitting in front of a high resolution monitor. So this is what these impressed marks might look like on our breech face impression. I hinted about those aperture shears a couple slides ago. Let's look at this area right here. Zoom in a little bit, and just for comparison. So here is a 3D image or 3D scan of those aperture shear marks. And remember, this is kind of the parallel of what I showed you at the very beginning for 2D images of the same type of mark. Now, full disclosure, these are different cartridge cases in the 3D and the 2D, but the concept is the same. Here we see these parallel lines matching up between the two items from a known match. And here we see the parallel lines matching up between the two items, again, in a known match. And I think you can probably agree, even with the screenshots, that on the left-hand side, it's a lot more detail and sharper image, easier for visualization than you can see on the right. And of course, both of these, as I mentioned, are screenshots, so it's better live. Of course, with a 3D image live, we can do a lot of really neat things like move a virtual light around, extract profiles, and so on. And we're going to talk a lot about that. So some of the strengths of 3D microscopy compared to the 2D is that with 3D microscopy, we're going to measure the high resolution surface, which is going to accurately represent that object, right? So we're going to measure that surface at, let's say, the micron scale, right, a millionth of a meter scale. That measurement, because it's XYZ points, is independent of lighting conditions. Whereas if I went back to this image, as I move the light around, these striations are going to come in and out of contrast. Some of them will get washed out. The measurements can be made traceable. And traceable means, as you heard from Brian, that you can relate this measurement back to a gold standard through an unbroken chain of calibrations. And what it means is that a micron is a micron is a micron. And I can compare scans from one system or at one site to another site if they're traceable measurements, if they're exchanged in a common file format, which is called X3P, which is an ISO standard. So you can make these measurements, make them traceable so we know the scale is correct, and we can save them in a format that allows us to exchange them between systems in a much easier way than you could do without 3D images. It allows a bunch of really neat features for comparison, these augmented comparisons, which I'll show you through most of the presentation. And it allows us to build statistical models that you really couldn't do with a 2D score. So there's a lot of big strengths. Some of the weaknesses are, of course, because this is a new discipline, you do require new equipment, so specialized equipment. Initially, those were slower to acquire than a 2D image where you would just stick your cartridge case under a light microscope and put your eye on the top and you're done. And of course, because this is more data, rich data, high resolution data, it results in larger data files. So the data files here are, between 20 and 100 megabytes for each single image compared to something a lot smaller in the past. Now, I would argue that most of these weaknesses are not really a big problem anymore. So our system, is actually relatively quick at the acquisition speed. Yes, it does require special equipment, but now there's a number of equipment to choose from. And the data files, well, hard drives are relatively cheap today. And so adding a little bit more storage capacity or an external storage device is really not a barrier to going to the new technology. So once we have these 3D images, there's really kind of two things we do with them. The first is called virtual comparison microscopy. And I know you've already heard this, but just formalizing it, the visual examination of a digital 3D microscopic representation using a computer and typically without physical access to the specimen. Because you'll remember from that initial paper with the virtual microscope, once that scan is acquired, that physical specimen can go back to the archive, which might mean an originating agency that could be in a different city, county, or state, or maybe the archive that's some other place on your site, but a different building. Once that scan is acquired, we don't need to look at that again. And the second half, besides the comparison microscopy where a human examiner is going to be at the helm, is to have algorithmic-based comparisons, where an algorithm is going to compare specimens using their 3D surface topographies for the primary purpose of establishing a quantitative measure of similarity. So in the remainder of my presentation, I'm going to spend about half of it talking about virtual comparison microscopy and about the other half talking about algorithmic-based comparisons. So the 3D virtual microscope is designed to essentially replicate, at least initially, the traditional microscope, light comparison microscope. And this is what the software essentially looks like. You'll notice we can load up two surfaces. We have controls on the left, which will allow us to rotate and translate those surfaces around, to zoom in and out of those surfaces, to adjust a virtual light position, to scale the images, to adjust brightness and contrast and things like this. So a lot of those basic functionalities are essentially the same thing you would do with a light comparison microscope. However, your surface is a bit more detailed. And then, as you'll see, there's a bunch of other functionality that you can't typically do on a traditional scope. And we'll see how that gives more power to the examiner. It all starts with having some image acquisition hardware. And again, Brian Renegar spoke about this yesterday. This is the system that we've been developing, and really, without going into any detail on it, it accepts a batch scanning tray, so you can load up multiple specimens. You can collect all those scans, and once you get those digital data files, we then can move into the software side, which I'm going to talk about. So we got our scans. What are we doing? So we came up with a list of about 5 ideas, probably about 5 years ago, for virtual microscopy. Since that first list came out, the first 4 of them have actually been reduced to practice. They're actually in use every day in some labs around the country that have moved to virtual microscopy. And the 5th one is still a bit emerging. So let's talk about these. So the first is what you would have expected, right? Comparing and archiving evidence. So you have instant access to remote or historic data, and you can use this access to reach source conclusions. Was it the same firearm? To write reports or document those conclusions and findings, to perform triage, for example, sorting specimens to find the number of firearms that might be present, or the best exemplars that might end up in reports or national databases, confirming database hits, and doing visualizations as, again, part of the documentation process. So this is what you would expect you can do with virtual microscopy, and it's what most labs will start with. Another application is training. So training allows you to have access to the best training samples, not typically what you have locally. So for example, if you're training at one location in the country to be a firearms examiner, you'll have access to all the test fires that they have at that location. They may not have a really interesting but relatively rare test fire that happens to be in another lab across the country, and vice versa. So you kind of had access to what you had access to. But with virtual microscopy, if you were to scan those images, and we're starting to collect these types of sets, then anybody can download that 3D data and compare this relatively rare phenomenon that they don't have locally, but they have access to virtually. It also allows insights to corrective action or corrective training if there's an error made during the training process. And I believe Todd gave an example of that yesterday from a study that we did, so I won't repeat it. Virtual microscopy can also be used for validation studies and proficiency testing. One of the big criticisms of a lot of the validation studies and proficiency tests is that there is sample-to-sample variance, right? Each person who participates in the proficiency test or validation study gets a slightly different test fire because they're physical items. With virtual microscopy, everyone gets the same exact file, and I'll show you an example of that. Fourth use is verifications, blind verifications, and overall tech review. So not all labs do verification or blind verifications in all casework. Verification is the process, right, by which a second examiner comes in and either reworks part or all of the case that was just worked by the first examiner. Both of the examiners have their results then compared, and if they agree, that's a good quality control check. If they disagree on their findings, then someone is brought in to resolve that conflict. This can be done in a blind way where the second person doesn't really know anything about what the first person did, or it could be done in a non-blind way where they see it. Obviously, a blind verification is better, and being able to do blind verifications on all conclusions is even better. And virtual microscopy really supports that because of the way we can hide work of the first examiner when the second person comes in, and also the fact that that second person can possibly be remote. So if you're a state lab system with 3 or 4 labs, it's possible that there is a capacity in one of those labs to do some tech reviews, but the other 2 labs are getting slammed with casework. And finally, the use that is just emerging now is the computer-aided verifications and establishing statistical confidence. So as I said, we're going to spend the last chunk of the talk on the computer-aided verifications. So let's start with some examples of what software can do in terms of like emerging tools for comparing archiving evidence, and then how that can be used also with the verification process. So as I mentioned, this screenshot here is the basic version of virtual comparison microscopy, and it has those basic features. But there's a lot of really neat things you can do, and I'm going to highlight a few. So with virtual microscopy, you'll notice in this screenshot, there are 6 active view panels. Each of these view panels are interactive. They're not in this screenshot, but in the real world, you can click and drag them around. You can move the lighting around. You can color the surfaces. So here, the examiner is not restricted to simply comparing 2 items at a time. They can compare up to 6 items at a time. And if the examiners really wanted, we obviously could split the screen up more and make 10 panels, but we stopped at 6. In addition to having multiple panels up, you'll notice some of these items are colored. They have colored title bars or colored thumbnails here. And that indicates, at least in this visualization, that the examiner has linked them as having common source. So all of these 3 blue scans, the examiner believes are from the same firearm, and these red scans are from the same firearm. So having this instantly available from the documentation process really helps. Another cool example is being able to document your work through surface annotations. So here what we see are some areas of the surface which have been highlighted by clicking and dragging with the mouse. You can use different colors. You can indicate areas of similarity and difference. And again, this goes into the whole documentation process. With respect to verifications, all of these assignments, for example, these color assignments and these annotations, can be hidden from the second examiner when the second person comes through to do that verification. That's a little hard to do perfectly in the real world with physical specimens. Another neat example is being able to extract things like surface profiles. So here are some of those aperture shear marks again. That's the rake and the sand type of tool mark. You can see some of the lines here even in the screen, small screenshot. But you can extract a cut profile through here, and that's what these red and blue curves are. And you can see what those profiles, how well they match up for the 2 specimens. Here, I'm not even necessarily using a score to tell me how similar they are. All I'm simply doing is showing them, and the examiner can slide them around. This is, again, something you couldn't typically do with a traditional scope. You can also have the computer augment areas of the surface to show you areas of potential similarity. So here are 2 test fires. They are from the same firearm. Hopefully you can see a lot of the similarity, even if you're not a firearms examiner. But what I can do is color the surface. So here, the algorithm has colored the surface, and it is a darker shade of this purple blue where there's more geometric similarity identified by the algorithm. And there's lighter shading or no shading when there's little or no similarity identified. So you can see some of these stronger filing marks that are colored in dark blue. And you can see this little patch right here where there's marks on the right surface, but not so much on the left, and it's not colored. So drawing your eye to those types of features, something again you can't easily do or can't do at all on a traditional scope. And of course, the documentation process. I believe Todd showed you how this is done yesterday. And one of the neat things with software that can keep track of this is that you're not going to make a mistake when you're labeling a particular specimen because it's tied to what you're looking at on the screen. So if you're describing particular features of a scan and you pop up a note right next to that surface, it is directly tied with the object you're looking at. So these structured case notes, of course, also get away from notes that might be handwritten and therefore difficult to read. And of course, they can be added to your laboratory information management or LIMS system. For archival purposes, they can be digitally signed and distributed. So this is great. And hopefully all these features you think are interesting and will help advance the field. I'll tell you a bit about that. But before we can actually use any of these tools, we need to obviously validate the tools. We need to validate the hardware, which you heard a little bit about yesterday. We also need to validate the software. And then, of course, any person who is going to use the hardware or software really should be competency tested before they actually use the technology. Labs are working on protocols for doing that and standard operating procedures for doing that. I'll talk about that at the very end. We've completed a number of validation studies that I can tell you about at a high level that are related to our technology, some of which we were directly involved with, some of which were other labs. And again, if you do your literature search, you'll hopefully find as the years go on, more and more of these studies. So the first study I'll tell you about is one completed by the FBI Firearms and Toolmark unit. Eric Smith is the technical lead. I believe he's speaking later in the week. And Eric Smith, as the technical lead, created a validation study for the Firearms and Toolmark examiners at the FBI, made up of previous casework and items selected from the reference collection. They were blinded, and the examiners worked through all of these scans. And the result, after they crunched their results, was that virtual microscopy was as good or better than light microscopy. They passed their internal quality controls, and they went live in 2017 using the system in casework. Our first study we published in 2018 in the Journal of Forensic Science, so a peer-reviewed paper. We had 46 trained examiners from 15 laboratories look at 7 test fire test sets and had no errors on their analysis. This was our pilot study, as you'll see some of these others that are much larger, to demonstrate some of the tools that we used to do these types of studies and to show that there was no errors in this base test. The next study, the larger study that we published, it came out in 2021 Journal of Forensic Science, and we presented it at a number of conferences, is the Virtual Comparison Microscopy Error Rate Study, or VCM-ERS. Here we had over 100 different participants from around the world, most from US and Canada, but a few from around the world outside. Each of those participants looked at 40 test set triples. So each of these test set triples were 2 knowns and an unknown. And again, the task for the participant was, does that unknown sample come from the same firearm that gave you those 2 known samples? And this type of a study design is one that was favored by people who may have been critical of some of the other designs, which they didn't like the way they were structured because it was not as similar to casework. So this is more replicative of casework. The error rate in this study was between 0.1 and 0.2%. And if you compare that error rate to traditional light comparison microscopy studies, we're on the lower end of that. So between 0 and 1.5% errors on traditional light microscopy error rate studies. Depends on who's involved, what types of firearms are involved, what types of ammunition, et cetera. So you can get a big range in there and it can still be correct. But here we are at the bottom end of that. And if you watch our webinars or read our paper, you can see the errors. We do a cause analysis of them to get to the bottom of them and understand how they happened. And the result of this study is that we concluded that virtual microscopy is indeed a valid technique for rendering source conclusions. In 2018, the Royal Canadian Mounted Police completed their internal validation study, and they published this. It's actually an early release right now, and hopefully in the first quarter will be official. But it is on, if you go to Journal of Forensic Science, you can get the early access to the paper. John Marshall and Laura Knowles did this with the 13 firearms examiners in the RCMP, 50 pairs of test fires, concluding that virtual microscopy gave results as good or better than light microscopy. And most recently, and slightly related, is the virtual comparison microscopy topography resolution study that we have a paper in prep for, and we've presented at conferences, looking at the effect of scan resolution on inconclusive rates with over 100 participants. So, this is where we kind of stand today in terms of validation work of the technology from the software and examiner side. And I think what you'll see is over the next several years, more and more of these papers be published, many of them by the labs that are implementing them themselves, some of them perhaps from academia, and others kind of from industry and industry collaborations. So let's come back to our list here of uses of virtual microscopy and kind of hit a couple other points. So I mentioned for training and validation studies, one of the shortcomings of traditional approaches is that you need to have a set of test fires for every participant. And this means that we need to have thousands of test fires collected. We need to send thousands of test fires to the mail, which may not even be legal if you're sending to areas where you can't send cartridge cases to the mail. There's concern about sample to sample variability, and the test taken by person 1 is not exactly the same as the test taken by person 2. But of course, with a virtual microscope, what we can do is take one set of test fires, scan them, and then distribute them electronically. Everybody gets the same identical surfaces. And of course, we wouldn't use floppy disks. I just like to put some nostalgia computer stuff in my presentations. This is all distributed, of course, over the network, over the internet. And that's how we've done the VCMers and VCM-TRS study as well. The validation studies with virtual microscopy also offer a really cool insight into the decision-making process. So rather than just simply asking the participants, are these from the same firearm or different firearms? We can also ask the participants, can you tell me exactly why you reached the conclusion you reached? So turning these black box studies into white box studies where we understand what's happening inside the brain, or at least a bit inside the brain of the examiner. So how does this work? So say an examiner was presented this pair of test fires. We would ask them to color the surface to indicate the areas of similarity and difference that they used in reaching their conclusions. So here, this blue-green might indicate areas of similarity, and the red and the orange might indicate areas of difference. So then what we'll do after the participants have completed their annotations is we look at the unknown for each test set, not just from one person, but from all the people that saw that same test set. And then we combine them into a summary annotation map. So on the right-hand side here, you see this annotation map where the surface is colored. Areas of the surface that aren't colored, nobody really marked. Areas that are marked in cool colors, a small percentage of people marked. And those that are marked in the warmer colors, the yellow, orange, red, are areas that many people marked. We can make two of these maps. One for the areas people marked as similar, that's our similarity map. And one for the parts of the surface that individuals marked as different, that's a difference map. So in this example here, and it doesn't really matter where this comes from, but this is from one of our validation studies, you can see this mark right here, this mark right here, this mark here, and then the entire aperture shear as being marked often by participants. And now we think this is actually a really neat conclusion. This is an insight that, again, we never been able to get without virtual microscopy and all the error rate studies that have been done in the past. This is cool because each of the participants worked independently, right? The 100 people who participated in this study worked independently. And yet when we combine all of their annotations, this is what we got. It's not like they all went into a room together and reached consensus and walked out with this map. They all worked independently. So we think that's actually really neat to demonstrate consistency within the examination process. Okay, so in the last chunk of time, before I start summarizing everything, I want to talk a little bit about comparison algorithms. Again, you've heard a little bit about them. The first thing to note with algorithms is that they're not going to solve every problem. And I like this cartoon. XKCD is a funny kind of science and math, kind of a nerdy cartoon, if you haven't seen XKCD. So here we have this person saying, hey, our field has been struggling with this problem for many years. And this computer person says, hey, I'm here to solve it with algorithms. 6 months later, hey, this problem is really hard. And the person, the expert says, yeah, you don't say. So this is true in almost any area where it's a hard problem and someone thinks they can solve it with just generically something simple. So algorithms aren't going to solve every problem, but the algorithms are going to be useful for addressing a few main uses. So what are those uses? So an algorithm, basically this mathematical construct, right, takes as input surfaces and it spits out typically just a score. And that score quantifies how much geometric similarity there is, or maybe how likely they are to have come from the same firearm. But in addition to that score, most algorithms, or many algorithms, our algorithm, can also give you an alignment that best orients these two surfaces, right? So I have these two surfaces, I can figure out the orientation that best aligns them to get the highest score. And it also perhaps can spit out areas of the surface that it thinks have the most agreement or least agreement, kind of like those annotations that I showed you before. So with those three tools, the score, the alignment, and the annotations, there's a bunch of really neat things we can do. So the three uses are, use one, searching a database or database search, which is essentially a recall function, and I'll show you how that works. Second use is coming up with pairwise statistical scores to tell you how likely the two surfaces are to have come from the same firearm. And the third is kind of independent of those scores, and it's visualizations and alignments and tools that will really help the examiner, even independent of what the numerical score is. So let's look at these three uses and see where we stand. So for database search, you have evidence that comes in, right? We take those items, we're going to scan them on a machine, we'll submit them to a database of other scans. We'll then get a list of candidates out, and then we can walk down that list of candidates, comparing the items that matched against my query. And we can do that comparison either using a virtual microscope if we validated it in our lab, or maybe we need to actually go back and actually get the physical specimens if this was a lab that hasn't done this yet, and compare the actual physical specimens under a traditional comparison scope. And in fact, this use one, database search and recall, is what we've been doing since the last 30 years, right? When I introduced DrugFire and the IBIS/NIBIN system, this is how they basically function. Of course, they don't use virtual microscopy here. They simply take an image, 2D images, search a database, get hits, and then look. But if we move over to 3D across the entire pathway, we can do this more efficiently. So this is use one, and this is essentially what's kind of in use today. Use two, the pairwise statistical correlation, is kind of right on the cusp. This is what Hans mentioned yesterday. So a pairwise statistical correlation would allow us to hopefully make statements like this purple text in reports and testimony, stating things like 2 cartridge cases, items 1 and 2, were compared and found to have similar microscopic firearm produced marks. The false match probability associated with a quantitative match score is approximately 1 in X, and this analysis provides strong support that items 1 and 2 were fired in the same firearm. Now this X could be 1 in a million, could be 1 in 100,000, could be 1 in 1,000. It depends on the strength of evidence that we have. But coming up with this false match probability or a likelihood ratio or a probability would actually be really useful in this type of documentation. And you'll notice that in this statement, this is a quantified statement of statistical support that we can't really make today. Now, of course, we need to do this very carefully. There's a lot of challenges in doing this carefully. And Hans mentioned a bunch of this in his presentations. But how would you use such a model if you actually had one? Well, if we go back to our workflow of using the database search, what we can do is move this over here and stick in a statistical score here. And of course, it's not the only way you can do this. In this scenario, we would have items that were scanned and maybe all the items from a particular crime scene. We ran through the statistical score and we found potential hits, and then we would look under our virtual microscope and reach conclusions on our own and go back and forth. Or maybe we actually submit those scans to a database, get hits, top candidate list, take those top hits and throw them through the statistical score. Or maybe we even bypass some of that. We just go directly from the scans to the examiner and back. So there's a lot of ways you can use these tools and a lot of thoughts that need to be given to, a contextual bias and making sure that we use the tools correctly and reach the highest quality conclusion. Now, I haven't talked a ton about kind of how the statistical scoring will be generated. How do we actually get such statistical score, and why is that score different than a recall score? So in a perfect world, the same algorithm that you use to search a database could be used to come up with a statistical score, the 1 in 100,000. But it may turn out that it's not the case. It may turn out that we need a very fast algorithm to search large databases of tens or hundreds of thousands of scans. And then we can use a slower algorithm, one that might take an hour to run, to compare just a pair of cartridge cases on a smaller number. It might also be the case that these types of statistical scores require human intervention to ensure that the number comes out as correct, meaning more manual guidance to guide that process than you would by just slapping it through a database search. Either way, how do we come up with the statistical models here? And again, this is something we spend full day workshops on just to scratch the surface. So obviously in the 5 minutes here, we can't do that. But the basic idea is we want to collect lots of test fires from lots of different firearms. That means that these firearms should be full range of makes and models, manufacturing types, ammunitions, and marking strength that you would see in casework. We scan those test fires. We then compute their scores. In this case, you have perfect separation between high scores for the matches and the low scores for the non-matches. Of course, that's not very realistic. And then we determine statistics. And this entire process is a model that we then need to validate and then test and then hopefully generalize to the real world. And we've been working on this. Other labs have been working on this in terms of reference collections that have been scanned. And we've been collaborating with the FBI, the RCMP, a number of city, state, and county labs. And a lot of the scans that we've collected and others have collected have gone into the NIST Ballistics Toolmark reference database, which is run by Alan Jen at NIST. And we've had some funding from NIJ as part of some of the research questions we asked to contribute this way. So this is something that's still emerging over time. Another effort that's looking at this is the Rapid Fit, which you'll hear from Alan in a couple of days, I believe. The Rapid Fit is a consortium between the NIST, FBI, and Netherlands Forensic Institute, or NFI, to help build some of these statistical distributions. So this is still emerging. This is something that's coming over the next many years. We're not there yet. And the final use of algorithms is to facilitate the examination process. So I'll show you 3 little uses and show you some fun videos, and then we'll start to wrap up. So one of the uses of algorithms is to do triage on items or specimens that come in regarding potential source. So let me tell you what that would essentially mean. So here's a video I'm going to play in a moment from our software. In this video, each of these circles and squares corresponds to a scan, a cartridge case that's entered into the system. At this point, this is the beginning. There's a red line, a red dash line connecting scans because the algorithm hasn't looked at that pair of scans yet. As I run this video, basically what had happened is that the algorithm is going to be run on all these pairs, and the red dashed line is going to be removed and replaced with a nice solid short line if the algorithm believes that those two specimens are from the same source. And it'll be just removed and replaced with nothing if the algorithm believes that they are from different source. So let me play this and you'll see how it works. So this is a 4x speed up. In reality, it's a little bit slower. It depends on your computer, etc. But here's the general idea. So once we're done here, you can see what happened. Of these 10 different cartridge cases, the algorithm believes that these 4 cartridge cases are from one firearm, these 3 cartridge cases are from a second firearm, and these 3 cartridge cases are from a third firearm. So you can see that here. Now an examiner can kind of come in and click on these links and examine them on their own to see if they agree with them. It's possible, for example, that you can, these little stars indicate the best marked representative from each cluster. So those could be used in reports or submission to a larger national database. Of course, questions need to be asked, when do we do this analysis? This looks like a really nice thing that can be done as part of the verification process, but it could also be used by a technician, not an examiner, before any of the examination takes place to select items or to give some triage information. For example, we believe there are 3 firearms present. So this is a triage tool that an algorithm can give us that's really separate from that statistical score or a database score. The next thing that we can do to facilitate examination is to use the alignment identified by the algorithm to basically give us this micron scale perfect alignment, and then use a virtual prism line, which is this divider line, swiping it back and forth to reveal more or less of each of the 2 surfaces. I'll show, if that didn't make sense, I'll show it to you in a video and it'll make sense on the next slide. When you're doing this type of alignment, it also can be useful to visualize the surface by coloring the surface. And I already showed you this purple coloring where the darker shades of purple indicate more geometric similarity. But there are other visualization modes. Here we have more of a rainbow coloring that indicates different features. We can extract linear profiles and so on. So let me show you what these might look like in some videos that are kind of fun. So here, I'll start the video and it will repeat. So on the left-hand side, we have one cartridge case, and on the right-hand side, we have a separate cartridge case. Both of these cartridge cases were fired through the same firearm. It was a Glock 23, 40 Smith & Wesson caliber. And as you can see, as we drag this dividing line back and forth, we're exposing more of one scan and the other scan. They are 2 separate scans. If you look up here, you'll see the left cartridge is relatively smooth here, and on the right cartridge, you see there's a gash there. So these are 2 different surfaces. But you can really see, because the algorithm has aligned these to the micron scale, how well the features that are reproduced from one cartridge appear also on the other cartridge. So you've got to sit, if you're an examiner, you can sit here all day probably and watch this and see how neat that is. Now you can do this visualization even without the purple heat map and simply slide those back and forth. Another really cool visualization mode we have is for those aperture shears, those striated marks I showed you back at the beginning. So here we have 2 aperture shears. You can probably see the similarity in the surfaces. At the bottom are the extracted profiles. So if I took a slice through these profiles, I have a blue one and a red one corresponding to these 2 surfaces. But in the video, when I play it, what will happen is the examiner is going to drag this black indicator line through the profile. And as they do, they're going to highlight different areas of the surface that correspond to the peaks. So for example, as we drag this line, you see that the green line is moving. And so you can stop on these different peaks and see what it corresponds to on the surface and vice versa. And that really helps you, again, in terms of the visualization, giving you a correspondence. This type of a view is something, again, you could never do with a 2D image. And these images can all be saved and put into your reports. Here's one final video, and I've put some arrows in here to cue your eye into some of the surface features again. So here we do not have the heat map on, but we've aligned them perfectly. And you can again see when you slide back and forth, the similarity that's present. So this is a really neat thing that we can do using algorithms to facilitate the examination process. Now, before I summarize, I should really say something about machine learning. This is something that is moving into a number of areas of society, of course. And you hear machine learning, you hear big data, and you think, hey, this must be used in forensic science. But to be honest, I'm not sure how well it applies in forensic science for a couple of reasons. I should say that I am a computer scientist, and the universities that I was in as faculty before I came here, it really is a machine learning, capital of the world, so to speak. And so I do like these methods, but I'm just thinking that within forensic science, there are some things we need to be careful of. So the first is the risk profiles within forensic science are a little different than they might be with other applications of machine learning. So for example, if you have an algorithm that identifies a dog as a wolf, or it identifies you as your sibling, and it's only for labeling family photos or a fun app on your phone, it's really low risk. Of course, this is very different within forensic science if you get something wrong. Of course, there are new areas within artificial intelligence or machine learning, like self-driving cars, where of course an accident would be really catastrophic. And so there are some areas within machine learning that may be more applicable, although some of these areas don't use all of the tools. The second is that related to this risk profile is a need for interpretability. So an algorithm which can give you an explanation for how it reached the conclusion it reached instills confidence in that algorithm and helps us improve that model, because if it makes a mistake, we can see why it made the mistake. And so, for example, those heat maps I was showing you really give us that insight. There's a number of famous examples within machine learning and object recognition where these single pixel attacks are oftentimes called, make one image look completely like a different image to the algorithm. Like a school bus is completely recognized as a dog, even though it's completely not a dog. So there's these weird blind spots sometimes that are problematic for us. And finally, we're really not big data. So even in the best case, we have hundreds of thousands of test fires, not the billions of data points that you typically need for machine learning. So we're not really there yet. Now, this is all not to say that there's nothing we can learn from these disciplines. In fact, we do use a lot of the ideas from machine learning and statistics. Machine learning is essentially applied statistics. And we use a lot of those tools within all of the models that we and others within the discipline are developing. But it's not quite as simple as, hey, I have this really cool app on my phone that does some recognition of animals, and therefore we should use it here. So this is still an emerging area, but this is just my take on it. So the 10,000 foot view, hopefully now this all makes sense to you. Cartridge cases come in, we can scan them in 3D, we get the 3D data, and then we can do a bunch of things with them. We can either examine them using virtual microscopy on our own, or we can hit them against a database or computer comparison score, and maybe go through some statistical models, and then maybe that cycles back to the virtual microscope and back and forth. So in summary, this 3D virtual comparison microscope as an emerging technology really gives us an accurate 3D microscopic representation of an object. It's moving from the research lab into the crime labs, and a number of labs are now using virtual microscopy in casework. It can be used for a number of applications, primarily determining source conclusions, but also for training, as we saw, for proficiency testing, for verification, and for statistical scoring. There's a number of things you can do with virtual microscopy that you can't necessarily do with light microscopy. So for example, the instant access was obvious. One thing we didn't talk about are saved and restored views, but software may allow you to, or can allow you to take however you've oriented your surfaces and lock it in, and then come back the next day and just restore you exactly where you were. It's as if you had remembered exactly which specimens were on your microscope, your light microscope, exactly how you had your light set, exactly how you had your optics set. Surface annotations, those coloring for linkages, remote access, and structured case notes. Again, items that will help improve the overall work product of virtual microscopy. And the validation studies that have been completed to date really do support this. It seems that the validation studies that have been completed, these are studies that have included now almost 200 and some participants, that they have virtual microscopy has similar or lower error rates than traditional microscopy, and likely much lower inconclusive rates than traditional microscopy. Finally, algorithms that we're going to use for within the discipline for search of a database, for determining statistical scores, or facilitating examination should be generalizable. As we mentioned, they need to generalize to work on real world data. So we need to collect scans from lots of different types of firearms and lots of types of ammunition. And they should be explainable or interpretable so that we get some insight into what the brain was thinking when the conclusion was reached. So where do I think what's going to happen over the next couple of years? So first, most, if not all, labs are going to move to 3D imaging to complement, but not necessarily replace, their traditional microscope. Labs are going to use this new software functionality to facilitate the examination and documentation process and to overall improve the work product. Population databases are going to be built with multiple scoring models in use, each of which maybe has slightly different performance. And these statistics will begin to be used in reports and in courts in some, but not all cases. This is something that we spend a lot of time on our workshops on statistics, that it's not every pair of cartridge cases can we come up with a statistical score for. But even if we can do that for about half of them, that's going to be really useful, because today we can do it for none of them, essentially. Additional validation studies are definitely going to be completed and will be published, and blind verification is going to become more common because it's going to be easier. Standards and guidelines are already being introduced to help establish best practices. So, this is not necessarily looking to the future, because OSAC, Organization of Scientific Area Committees, within NIST, is already published 3 standards for virtual microscopy or 3D imaging. Another one for virtual microscopy is coming out soon, and the 3D Technical Working Group is already producing guidelines. So this is where we are in terms of emerging technology. While just the part of what I talked about is in the future, most of what I talked about actually is here today. So here's our acknowledgement slide. And again, my team at the top here with Chad, Eric, Pierre, and then our collaborator, Todd Weller, a number of labs we've worked with for a number of the projects. If you want to learn more about what we're doing, you can get that information here, and this information or this link or email will get to me. Thanks.
Thank you very much for your presentation, Ryan, and also for starting with a nice historical perspective. Let's move into the question and answer session. And as a reminder, please type questions into the chat now. Ryan, for our first question, if a second examiner or reviewer is not available in the lab, can we totally rely on VCM regarding comparison results?
Right, so I think that question is thinking about whether or not the second person, the second examiner, can rely solely on the digital image and not have to go back to the source specimen. And so that's going to depend on the lab and what you've approved. So I can say that some of the labs that are using virtual microscopy today, once the scan is acquired, the entire conclusion can be reached off of the virtual image, and they do not need to go back to the physical specimen if there's enough information on the scan that's been acquired. If the scan only provides them enough information or doesn't provide them enough information to reach a conclusion, then they will go back to the original specimen and look to see if there are other secondary surfaces or marks that they can get to. So for a lab that has validated virtual microscopy for reaching source conclusions within the lab, I think that if that second verifier is off-site, then they should be able to reach conclusions as if they were on-site.
Great. And do you happen to know how much data storage would be required for the 3D data produced by a typical laboratory's Firearm and Toolmark caseload?
Yeah, so when I saw that question kind of came up, I was thinking, okay, so what is a typical lab? Labs are all different size. So some labs may do 1,000 scans a year, some may do 10,000 scans a year. So a scan is typically about 50 megabytes. I think I mentioned that in the presentation. So if a lab does 2,000 scans a year, then that's about, I think it's 100 gigabytes of data. So 100 gigabytes of data is nothing today, right? You can get a terabyte drive for like $100. So you do need to think about the data storage and backups a little bit differently than you do for non-3D data, but the actual storage capacity really shouldn't be a limitation today.
Great. And in the validation studies results, is the number of years of experience of the participants taken into account?
Yeah, that's a really good question. So in our studies, we did 2 things. So we separated those participants who were trainees or non-qualified firearms examiners into one pool, and those that were qualified firearms examiners into a second pool. And the idea is that if you were a trainee, you may be the first day in the lab and someone said, hey, do you want to participate in this study? You say, hey, this would be fun. And of course, you don't have the same background in training as someone who's a qualified examiner. So for us, we did the first split of qualified examiner or not. Then within the qualified examiners, we did ask everybody for their experience. It's of course self-reported. And I think we broke it down into less than 3 years, 3 to 10 or more than 10 or something like that. So we do break it down that way. And I think each of the different validation studies will have different breakdowns and different ways of looking at it. But for us, the most important part was to separate those who are qualified from those who are non-qualified examiners.
Excellent. Next question. Do you think the results based on algorithms will be sufficient to defend in court?
Yeah, so that's a good question. I think Alan wrote a little response to that question when it was asked. So at some point, the algorithms will get to be very good such that they are part of the documentation package and can be cited. And the algorithm that's used will have been validated on large data sets. So for example, if algorithm X was used and reached a conclusion that said the false match rate was 1 in a million, And that algorithm X had been validated through several publications that were peer reviewed, tested on millions of comparisons, and had an error rate of whatever it is on that data set, then yes, that could go into your report or testimony and say, this is the algorithm that was used, and here's the testing of that algorithm. So I think we can get to that point. I don't know if it's something where you just kind of close your eyes and just transfer it over. I think it's part of the overall package. But I think just like as in other areas within forensic science, the algorithm or the mathematical score is just part of the story. I think it will become part of the story here.
Great. If you were to generate a 1 in X statistic, is that considering just firearms with the same class characteristics, or does it also consider all regions of interest collectively, or does it give separate scores for each?
Right, that's actually a really good question. So there are different types of scoring functions that can analyze different surfaces. So you might have a score that just compares the aperture shear, or just the firing pin impression, or just the breech face, or just a ejector mark. And those can have a score. And some of those scores may have more confidence than others. So for example, the breech face impression with a very large amount of area that the breech face impression is may have more statistical confidence to it than matching, let's say, a firing pin impression, which is a much smaller object. But the second part of that question is actually really insightful, which is each of these independent scores could get combined. So you'd say, I compared, for example, the breech face and aperture shear, and I got this much similarity, and the algorithm got that much similarity. I also, or the algorithm, compared the firing pin impression and got this much similarity. Maybe it also compared the ejector and got this much similarity. Okay, I'm going to combine all three of those. How likely was it that I had high similarity on each of these three different scores? And that becomes even more important when each of those surfaces are independent surfaces. So we didn't really get into a lot of, subclass, which is a big hot topic, of course. But if you have a breech face impression having high similarity, and then the aperture shear, which is formed by a different surface, and then the firing pin, which is again another surface, the likelihood that you have this collusion of subclass across all three surfaces is very low. So yes, combining the scores into a combined model actually is a really good idea, something that a lot of people are working on.
Thank you. And how big of a zone does the colorization algorithm use to show high agreement?
Yes, that's a good question. So there's lots of different visualizations we have. I showed you the purple one, which was kind of the first one that we developed, and is kind of the main one we use. In there, our algorithm is based on a couple different submodules. One of them looks at features on the surface of the breech face impression. The features that it looks at are different size. So they could be as small as a few microns in size up to hundreds of microns in size. So when we do the comparison between the two, we can find similarity between two surfaces. We can find similarity at each of those different levels. We then take each of those levels, glue it together, and get that image. And we do make it so that it's not quite a hard edge. So we kind of, just for visualization purposes, do put essentially a Gaussian edge onto it to make it a little smoother. Some of the other visualizations that we have are pixel to pixel. So you do have that harder edge to say these pixels align and these pixels don't. The other part of that is, of course, from test fire to test fire, there is a little bit of variability. It's not going to be identical. So if you have a ridge on one surface and another corresponding ridge on the second, if you were to align them, it's not uncommon that they would be a little bit off by like at the micron scale. And so having that fuzzier blue coloring allows you to see it a little bit better.
Great. How often do you calibrate your instruments?
So that's a good question. So our instrument, so calibration is a loaded term as well, because it two questions of what does it actually mean by calibration? So our system is calibrated, obviously at the beginning, at the setup time. And we use quality control checks through the process to make sure that we maintain measurement accuracy. So we use a microscale reference specimen that we send out to a lab that's an accredited lab to give us a calibration certificate. There is a process by which the lab at setup and then at any point in the future can collect measurements. There is a protocol for that is partially, it is consistent, of course, with the OSAC documents and standards that are published to establish your kind of uncertainty in those measurements. You then establish your guardrails to say, when I measure this microscale reference, I want to make sure that I'm within this range of allowed measurements. If you fall out of that range, you then repeat the measurement. And if you're still out of the range, then you can call us and say, hey, the system's not measuring within the allowed tolerance. But to do that, you need to have that calibrated microscale reference first and a protocol to do that, which at least for our system we have. And by following that process, because the microscale reference that we have is measured in a calibrated lab, that calibrated lab is producing traceable measurements. And as you kind of heard in Brian's talk yesterday, that means that those measurements are related back to a gold standard through this unbroken chain of calibrations, it essentially means that the measurements that we're producing are traceable. So that's the longer answer. The shorter answer is we have a quality control check process with a calibrated microscale reference to make sure that you're within the appropriate measurement tolerance.
Thank you. And would using a triage system not introduce a further risk of bias?
Yeah, that's a good question too. So the question is, when do you use that triage system? So say you use that triage system before an examiner, started looking at any of the items, and they use the information from the algorithm or the triage before they started their analysis. The person who asked the question is completely right. That could influence the examiner to say, well, I really trust the computer. They've always been right in the past. Algorithm linked these two. I'm going to believe that they're linked more than I would have if I didn't have that information. So many labs turn off the algorithm and turn off the triage function before the examiner has reached their conclusion. So the triage function, even though it's called triage, may be useful in those situations after the examiner has reached their final conclusion. When the examiner reaches their final conclusion for a case where maybe there are 50 specimens, they may not have had a chance to compare all 50 against all 50, right? Because that would be 50 essentially times 50. That'd be a lot of comparisons. So they may have compared a few of these guys over here, and then a couple over here, and somebody from this group to somebody from this group, maybe a few from here to here. So throwing all of those into the triage could perhaps do some cleanup or mop up in those situations after the fact. But the other use is for non-firearms examiners who may be having to deal with the evidence to decide what to enter into a national database system or to pass along to a second analysis. And so that first person who's not going to reach the source conclusions, they might use the triage and it might be okay. But each lab's going to have to really decide, when do I kind of uncover what the algorithm is telling me? And some of those what is it? The third one, the examination facilitation that I described, those uses, for example, the alignment or the coloring, could be used even without a numerical score. So these are things you still have to learn. That's why it's an emerging technology and not a well-defined technology, right?
Thank you. And then, do algorithms tend to analyze firing pins independently from the breech face?
So I can say that ours, we do. I think you should, because there's two reasons for that. I guess the firing pin could be floating and its orientation relative to the breech face may not be entirely consistent all the time. That doesn't happen too often, I'm told, although of course I'm not a firearms examiner, so I could defer that to someone else who knows. The other is that it is a different surface. So going back to the question from earlier, it's probably better to compare breech face to breech face using that function, aperture shear to aperture shear using that function, firing pin to firing pin using a different function, and then combining all of those as three independent measurements of similarity to come up with a cartridge to cartridge comparison.
Ryan, obviously by the quantity of questions we are receiving, we could keep you here literally all day, but
That's right.
That is all the time we have for the question and answer session. Thank you, Ryan, and thank you everyone for your great questions.
Sounds good. Thanks.